Okay, so what do we know about our devices when we're talking about routers? Well, straight away, these devices automatically know about networks that are directly connected to them. So this device here automatically knows about this network, this one, and this one. Now, if we want to have connectivity to remote networks, such as this one right here, we were previously doing things such as creating static routes in each device's routing table. Now, this allows us to be very precise about what we want to happen with respect to our paths. We can say, hey, if you're going to this particular network, I want you to go this particular way. That said, this is not the most scalable solution, especially if you're dealing with hundreds or thousands of devices. So as it stands, we want to actually utilize something known as dynamic routing. Pretty much this is code speak for saying we're going to be using a routing protocol. That is a protocol running on the devices that is going to allow them to automatically share information about what they know. Now, there are different routing protocols that you can use, but the one that we're going to focus in on in this particular skill is one known as OSPF. So the first thing to state is that OSPF actually stands for the Open Shortest Path First. Now, the cool thing about OSPF is that it actually is an open standard protocol, meaning that it's not specific to Aruba devices or to Cisco devices or to Juniper devices. Conversely, any networking vendor that wants to implement OSPF can do so within their own software. So it's really good if you happen to have multi-vendor environments. But what exactly is it? What does it do for us? Well, of course, it is a dynamic routing protocol. So if all these devices here are effectively utilizing OSPF, then they can use that protocol to, well, share information. No surprises there, but that doesn't really tell us how OSPF actually operates. So let's talk a little bit about the specifics. Say, for example, we have this device here and this device here. They can essentially start sharing OSPF information with one another and form a neighbor relationship. Now, specific routers in the network are going to actually form a full adjacency with one another. Now, in forming a full adjacency, what we're talking about here is sharing complete information about the network with one another. So if a link goes down, we share that information. If a network gets added or disappears, we share that information. So as these neighbors and adjacencies are formed, ultimately each OSPF speaking device is going to form what is known as an LSDB. This is a link state database. As it stands, this is really just going to give each device a detailed map about all of the other information in the network. So what that would mean is that even though these two devices could have a neighbor relationship and form an adjacency, even though this one here is not actually connected to this particular device, it's not just going to learn about its connected networks such as these ones right here. It's also going to learn pretty much everything about that particular device. It will know that this device has got these particular interfaces participating in OSPF. This device will know about the bandwidth on these particular links connected to this particular device, as well as this one's router ID, something we'll talk about very, very shortly. We'll know that this device connects directly to this particular device and this particular device. And this is going to be true for all of the devices in the same OSPF area, okay? Now this word here I actually used very, very specifically. This is a technical term in OSPF. So an area in OSPF terms is really just a logical grouping of OSPF speaking devices. And everyone in the same OSPF area is going to have an identical link state database. Quite simply, if these are all in the same area, this device will know everything about this one, everything about that one, and everything about that one, and the same is true for all participants in the same area. Now, in an upcoming skill, we'll talk about actually creating multiple different areas in OSPF and why we would do this. But for now, just understand that we have this concept of an area, and for OSPF, there is one area that absolutely has to be configured, and this is known as area number 0. This is sometimes referred to as the backbone area. Again, this is a concept we will revisit in an upcoming skill in a lot more detail. So essentially, all devices in the same area have the exact same map of the network topology. And if this device wants to perhaps get to this particular network, the way it's going to calculate how to get there is by using the SPF algorithm. This is the shortest path first algorithm, otherwise referred to as Dijkstra's algorithm. In its simplest sense, this is an algorithm that helps us get from one point of the network to the next point of the network by transiting the path with the best link speed. So that is the path that gives us the best bandwidth. Now the cool thing about OSPF having this link state database is that if anything happens within the network, everyone else is going to know about it. So if, say for example, this particular link died right here and this network is no longer available, every single OSPF speaker is going to know about it quickly. Now, one point I really want to emphasize here, let's say we happen to have these two devices, let me just get my pen back up, these two devices here, and we want to form an adjacency across this particular link that connects them. We have to understand that there are very particular rules at play that allow for this to happen. Now, for clarity, we will look at these rules in more detail in this very skill, but just as a rough overview, understand that each OSPF speaker in the topology is going to have what is known as this router ID. We just mentioned that. This is just going to be a numerical value that uniquely identifies the speaker itself. Now, these router IDs ultimately have to be unique, so if we have the same router ID on both sides of the connection, we will not get this OSPF adjacency formed. So very important we have unique router IDs, okay? In a similar sense, these devices here, when we are forming an adjacency over this link, we have to agree that both interfaces are in the same OSPF area. So if this interface says I'm in OSPF area 0 and this one here says, well, I'm in OSPF area 2, we will not get this adjacency formed. Now, across this connection here, another thing that has to be agreed upon is what are known as the timers. Specifically, each speaker is going to be sending what are known as hello messages, and by default, they are going to be sent every 10 seconds. Now, if you don't hear anything from an OSPF speaker, we're going to have what is known as a dead interval, which is going to give us some grace period, whereby we will wait a specified period of time before removing that neighbor relationship. So the default for hello timers are 10 seconds, and we wait 40 seconds for the dead timer. Now, if, say for example, this interface here happens to have a different OSPF timer from this particular interface, once again, we cannot have an OSPF adjacency formed. This is something, again, that just simply has to match. Now, another thing that has to match is that both sides of the connection must be on the same network space, and they also must have the same network mask. We'll see this very, very clearly in an upcoming video. Now, to be clear here, there actually are even more rules than that to form an adjacency, but those perhaps are a little bit more advanced and something we can revisit in an upcoming skill. For now though, those are the main components that have to be agreed upon to get our basic OSPF configuration up and running. Alright, so now we know some of the basics about what OSPF actually is. I think the best thing for us to do is to get hands on and begin configuring OSPF across our network topology.